Hey, welcome back to Leap Math. Today I want to talk about factoring by GCF. GCF stands for greatest common factor. So what we're looking for is if I have a certain number of terms, I want to know what is the biggest thing that they both have in common. So to do that, I sort of want to break them down into, we'll call them their prime factors. So as small as they can possibly go. Right now this is considered simplified form. I want to break it down into 3 times x times x. This, if I were to multiply it out and simplify it, 3 is the 3. X times x would give me x squared. So this term is kind of the expanded term. And then I'm going to add it with this one. And I sort of want to break this down. And with all of factoring by GCF, in order to help me, and what I usually tell my students to do, is to take it in 2 parts. First one, you want to look at just the coefficient, or just the numbers. So you're going to look at the number and figure out what the number has in common. And then you're going to look at the variables. So when I'm breaking this down, I always just want to look at the number first. So 6 is not prime. I can break it down further. 6 is really made up of a 2 times a 3. And those are both prime factors. And then there's an x, and that's the variable. And the x is just the x. So I've broken the 3x squared into 3xx, and the 6x into a 2 times a 3 times an x. Now the idea of a greatest common factor is that there is something that both of these terms, that this term and that this term, both share in common. They both have the same. So I look, and I always want to look at my numbers first. So this one only has a 3. So I look over here, that one also has a 3. So the 3 is something that they have in common. This one has a 2, but the one on the left does not have a 2. Since they don't both have the 2, that is not something they have in common. And then I look, and this one has at least one x, and that one has one x, so I'm going to go ahead and put a line under that as well. The one on the left side has a second x, but there's not a second x on this one, so the only things that they both have in common is a 3 and an x. So that becomes our GCF. This is our GCF. And when I factor by anything, factoring is sort of like undoing a multiplication or a distributive property. So if I divide both of these terms by this 3x, what would be left over? So that's kind of what I want to know, is if I divide them both by 3x, what is left over? So I have this 3x here, and whatever was left over is going to go in here. So this x was left over, so it goes inside the parenthesis. Then any separation you have with a plus or a minus still has to show up in here. Because if there's no separation, then we assume it's multiplied. So if there's a plus up here, I have to still show that there's a plus separating 2 terms. And on the right side, there was a 2 left over, so I write the 2 down. Now if I wanted to check to see if this matched, in order to check, I would distribute. So right now this would be my answer. And if I wanted to check to verify, I would distribute. So I would say 3x times x. So 3x times x would give me a 3x squared. And 3x times 2 would give me a 6x. And as long as that matches this, then I know I've done my math correct. Oftentimes, you don't have to write this step right here. If you can just see and know what they have in common. I'm going to show you the step again just so that you can understand where that step is coming from. You can see it in another example. So if I take this second example, I again want to break this out. If I think about this number, the number 4 is not prime, so this breaks into 2 times 2, and then there's an x, so I put the x. I need to have the plus. And this 12 is really, it's like a 3 times 4, but 4 is not prime, so it's really a 3 times 2 times 2. So if you're pretty good with your factor trees, that's kind of what we're making right here. We're just expanding them out. And then anything they have in common, that becomes our GCF. So here, they both have 2 2's. Since they both had 2 2's, that's what I underlined. The first one has an x, but the second one doesn't have any x's, so that's not something they have in common. The right one has a 3, but the left side does not have a 3. So, at most, they have that 2 times 2 in common. And we know that 2 times 2 is the 4, so the GCF for this problem is just 4. And if I do what I did for the first one, I want to think about what's left over. Well, this x was left over and that 3 was left over. So there's an x, the symbol between them is plus, and 3. If I were to double check this using the distributive property, because that's how you check to make sure that your GCF is correct, 4 times x would give me the 4x, and 4 times 3 would give me 12. So I know that that's good. Now, at any point, it's always good to practice on your own, so if you wanted to pause the video and see if you could do the next one on your own, that would be a good time. For C, I'm going to go ahead and skip this step, and I'm just going to try and see if we can do it without having to do all of those steps. So if I think about it, I want to deal with numbers first, and if I notice, they don't have any coefficients, or the coefficient's 1, so I don't really need to distribute or pull that out. So the next thing I look at is any of the variables. They're all multiplying, so I look and they both have at least one x. And then I think about what powers they have, because depending on how high the power is, like over here, the power tells me how many of those variables I have. This one says I'm going to have 3 x's. So if I were to actually write this out, I would have x times x times x. But the one on the right side only has 1. Remember, there's that invisible 1, always. So if I have 3 x's over here, but only 1 x right there, at most, how many would they have in common? Only 1. So I'm going to write that x out front. That's what they have in common. Then I move on to the next letter. My letter is y, and I have the same conversation. This exponent tells me that I'm going to have 2 y's. Y times y. Over here, I have that imaginary 1 exponent saying I only have 1 y. So it has only 1 y in common. Then, I don't have any other thing in common, so I'm going to go ahead and say that's my GCF. And here I want to think what's left over. So you can think about dividing it, or you can ask the question, x times y times what on the inside would give me this? And sometimes asking it in that kind of backwards fashion helps. So x times what would give me an x cubed? Well, this tells me I should have 3 x's, and I only have 1 x right here. So in order to get 3 x's, when I only have 1, I'm missing 2 x's. So I know that there's an x squared in there. In order to get a y squared, when I only start with 1 y, I need at least 1 more y. Then if I just double check this first part, x times x squared would give me an x cubed, so that part works. And y times y would give me y squared, so that part works. Now there's a minus between them, so I need to show that. Now on the next part, x times what would give me x? Well, there's 1x here and 1x there. So I don't need to add another x. I have enough x's. There's 1 y here and 1 y there, so I don't need to add any more y's. But I can't just leave this blank. I need to somehow show whoever's going to look at my problem that I need something over here. I need one of these terms to show up on the right side. So I'm going to use a 1 as a placeholder. That way if I say x times y, right, xy, times this 1 is going to give me an xy. So this would be my end result for that problem. And I did this in my head. I sort of knew how it would break down in my head, but I didn't write it down. So if it helps you to break everything down, go ahead and break it down. If you can do it without breaking it down, then you're one step closer to doing them in your head. But this is a good default. If you're not sure, break it out, expand it out, and then collapse it back. Like, that's always a good thing to do. Now I want to talk about some more complex examples. They just have more stuff going on. So again, first thing I want to look at is my numbers. So if I look at the numbers, I have a 6, an 18, and a 21. So a 6 is a 2 and a 3. An 18, well, that has a 6 in it, so that's good. But a 21 doesn't have a 6 in it. 21, if I break that number down, is 3 times 7. So the only thing I noticed that all three of these numbers had in common, because the 6 and the 18 did not have a 7, they only ever had a 3 in common. So I'm going to divide all of them by 3. I'm going to pull that 3 out front. That's part of my GCF. Now I look at my variables, and I want to look at my x's first, because we go alphabetical. So this has x cubed. There's 3 x's here. This one has 2 x's. It's an x squared. This one also has 2 x's. So the lowest number of x's, both of these have 2, and this one has 3. So I know they all at least have x squareds. Some of them have more, but all of them at least have x squared. And I want the biggest number that I can find. So x squared is the biggest that they all have in common. Now I look at my y's. This one has a y, and the last one has a y, but this middle term does not have a y. So they don't all have y in common. So I can't add that in my GCF. So now I write what's left over. Now, my favorite way to do this is to say 3 times what would give me 6. That tends to ask my brain the perfect question, for my brain to want to write down what the perfect answer is. So 3 times 2 would give me 6. And if I think about distributing it, 3 times 2 is 6. And that's what I'm looking for. 3 times something on the inside, like I'm distributing, would give me what's on top. X squared times what would give me an x cubed? Well, I have 2 x's and 3. I'm missing an x. So x squared times x, that would give me 3 x's total. That would give me the x cubed. And I'm not done yet. There's no y on the outside, and I need a y up here, so I have to have at least a y right there. The symbol says plus. Then there's an 18, and if I think about it, 3 times something would give me an 18. So in essence, I need to divide 18 by 3. So if I divide 18 by 3, I would get a 6. And then there's an x squared and there's an x squared, so I don't need to add any other variables. 6 is good. There's a minus sign, so I need to pull that minus sign down. And then 3 times what would give me a 21? The other way around is 21 divided by 3 would give me what? Well, there's a 7, and 3 times 7 gives me 21, so that matches. X squared gives me x squared. I don't have to add anything. But there's a y, and I need the y to show up, so that's my end result. If it helps you to break it down like this, or when you're double checking, you can think about it as You're dividing all of the terms on the inside of these parentheses not make a very pretty parenthesis. The only thing is going to make it look prettier. So pretty much everything on the inside here I got because I divided the original by what I thought was my GCF. And a good way to double check, besides redistributing it, before I get to this next one, because this one is an interesting thing to think about, is if I look at what's left over on the inside, I want to make sure that they don't have anything else in common. So here I have just an x and a 2, a variable and a number, nothing in common. A variable and a number, nothing in common. X squared y, so there's a bunch of variables, and a number, nothing in common. Here, the 2 and the 6 would have a 2 in common, but the 7's prime, so the numbers don't have anything else in common. This one has variables, this 6 has no variables, and that one would have a y, so they also don't share any variables in common. So I've done a double check on the inside to make sure there's nothing left over. Otherwise, you might have pulled out a common factor, but it might not have been the greatest common factor. So I know that this was my answer. I have factored out, I've pulled out that GCF. And if you think about it, it's like pre-distributive property. So I could multiply this out, and I would end up getting this. So for this last one, what I want you to imagine is what would it look like if instead of this c plus 2, if you had a variable there instead. So we're going to go off to Imaginationland, and I'm going to rewrite this, but everywhere I see this c plus 2, I'm going to change c plus 2 to just be like x. Because really, the quantity c plus 2 is just some number I don't know. C is a number I don't know. It's a variable. Could be 5, could be 10, could be 1,000,000. I don't know what c is. It's some number plus 2. And really, that's just some variable I don't know. So if I imagine what it would look like if it had an x involved, it would look like this. 5x to the 6th power minus 10x to the 4th power. This looks a lot simpler. And if I thought about factoring this out, well, obviously I would pull a 5 out, and then I would pull out some of the x's because I have 6 on this side and 4 on that side, so they at least have 4 in common. And it would kind of look like 5x to the 4 parentheses, and 5 times 1 would give me 5, so I don't have to write anything here. And x, 4 of them, and I need 6 of them, so I have 2 that need to go inside, so that 4 plus 2 is 6. Multiplying same bases, I add the exponents. Here, I have the minus. 5 times what would give me 10? Well, I need a 2 on the inside, so that 5 times 2 would give me the 10. And then I have an x to the 4, x to the 4, so I don't need anything else. And then I have just variables, just a number, so I'm good right there. This is how I would factor if that's what I had. I want to do the same thing with what I actually have. So I have a number, a coefficient, and I look at the coefficients first and I say, oh, well, 5 and 10 share a 5 in common, so I pull that 5 out. And then I have some quantity, and I have 6 of them over here and 4 of them over here. So my lowest number is 4 of those things, so I'm going to pull out 4 of those things. And then whatever's left over, and you could use another parenthesis if you want. You could use a bracket if it makes you feel better. I'll use a parenthesis. Either way, it's showing multiplication. And I need to write on the inside what's left over. So I have 4 of these. I need 6 of them. So if you notice, I need parenthesis again. Well, in order to use a parenthesis and a parenthesis, it might be easier if I went ahead and just made this into a bracket. Now I'll write c plus 2 squared. And if I had c plus 2 to the 4th and c plus 2 squared, it's some quantity that's the same base. I add the exponents, so I would get that 6. Then there's the minus. And then 5 times what gives me 10? Same conversation, it's a 2. And then c plus 2 to the 4th, I already have that, so I don't need to add it, then I'm done. And that would be my answer. So I wanted to do this problem to show you that even if you have a set of parentheses here, you can sort of think about replacing it to give you the idea of how you should factor it. This is the same format. If you notice, I had 5 something to the 4th power, something squared minus 2. The format was very similar, but what that thing was the thing that changed. So important things to take away from factoring by GCF. You can break it out into its prime factors, and anything that they have in common, that's what you pull out front. That is your GCF. Whatever was left over goes inside parentheses or brackets. You can check by distributing, multiplying it out if you really want to. You can also, once you think you have the GCF, in order to get what's on the inside, you can either think, GCF times what would give me this, or you can divide the original by the GCF. So 6 divided by 3 is 2. If I had x cubed divided by x squared, I get x. And then y divided by nothing is still y, right? 18 divided by 3 is 6. X squared, those would cancel out. And then 21 divided by 3 is 7, and then x squared cancels, and then a y on top. So I could divide each term if it helps you, or you can think about what would I need to multiply to get the original. Either way, I hope if you were struggling on factoring by GCF that this helped you. Remember to like, share, and subscribe. Have a great day.